One of the fastest growing professions in the computer industry is data analysis. Data analysis is basically the loading, the processing, and the analyzing of data, typically very large sets of data. This is done to help businesses grow, possibly to identify security weaknesses. The whole world runs on data right now. And Python is at the forefront of this revolution in computer science. One of the libraries which is heavily used in data analysis is called Pandas. And as you can see here on the pandas.pydata.org website, you will see information about Pandas and the most recent releases of Pandas. Now, Pandas itself utilizes other libraries as well. So there will be other things like NumPy, and it works hand in hand with another library called matplotlib. Now, all of these work together to help you analyze and visualize data. This is a large topic all in itself. Pandas and data analysis could take weeks just to start getting comfortable with it. So this is going to be the 10,000-foot view, as I like to say sometimes. We're not going to get too deep into the weeds, but I do want to show you some of the more powerful features, and hopefully it may spark an interest and it may help guide you in your career. So I will be working in Jupyter Notebook for most of these demos. It doesn't require it. However, later when we start looking at some of the visualization routines, there are some special things you have to do to make it work in Jupyter correctly, where you don't have to do that if you're working from the command line using the Python interpreter directly. So we're going to start looking at something called a series. And the series is one of the base data types that's heavily used by Pandas to store typically linear sets of data. And this data could be just a standalone list of data, just as you would do a normal list, or it could also be a list that corresponds with indices. And the indices don't have to be a linear position like you would in an array. It is in fact string-based, and they don't have to be unique. So this allows us to use things like dates for these indices, and then if we're going to graph things, we can graph things by date then. But I'm jumping ahead. Let's start back at the beginning. For this to work, you'll have to install Pandas, and typically if you have installed Python via Anaconda, you will have Pandas already. It's installed with most distributions, so most of the time you won't ever have to do this pip install Pandas, or possibly upgrade it by using this pip install upgrade command. But if you're having difficulty and the libraries aren't being resolved correctly because you have Python installed by several different applications and it doesn't know which version to use, then you can give it a little help by upgrading it. Once you have your Pandas installed, we are going to import several of the modules. We're going to first of all import something called NumPy. And NumPy is a highly efficient library that is compiled in C for the most part, and it's very fast, but it provides C-style arrays and other data analysis routines, which will always run much faster than possible in an interpreted mode in Python. So Pandas and NumPy rely heavily on these faster routines, because otherwise handling large sets of data would just grind to a halt. Now, it is not necessary, but it's pretty much a standard that when you import NumPy, you give it an alias of NP. When you import Pandas, you give it an alias of PD. It is not required, but like I said, it's almost a de facto standard in the industry, and if you were to go on Stack Overflow or most any other site, you will see them also doing the import statements this way. Next, I want to create a series. I'm going to call it S1 and I'm going to create a series object from the Pandas module, and I'm going to give it some numbers. And I'll just because I can't think of a more creative list to give it, I'll give it the first few Fibonacci numbers. And then I'm going to print this. Now, the first thing you'll note is it looks just like a regular list. And when we create these series, in fact, we are going to use that basic terminology. It is kind of a list. But in reality, these are arrays. And when they're handled on the back end, they are going to be treated as more traditional C-style arrays, which are much faster than the dynamic lists inside of Python. So let's go ahead and import those. Might take a few seconds, and then I'll run this. And you'll see it generates this output. Now, the neat thing about this output is you see two things. You see the list of numbers here on the right, 1, 1, 2, 3, 5, 8. But on the left is another set of numbers. These are the automatically defined indices or indexes for these values. And by default, they are zero-based and monotonically increasing, so 0, 1, 2, etc. And if we wanted to, and I'm going to actually put a break in here. A break, by that I mean just a series of equal signs so I can separate my output. And then I will simply call into the S1 series with an index of 4 and hit run. And as expected, it did return this 5. Okay, I could have put it in a print statement as well. But one thing I'm going to show you as we move forward, a lot of the data types in Pandas are handled specially in Jupyter Notebook, and they will be output using very special formatting. So when we get there, you'll notice it, and this is one of the reasons I like Jupyter Notebook. It does make it a lot easier to visualize the data. Okay, back to the task at hand. I'm going to create another series, and this series is going to be, instead of just the list of numbers, I'm also going to provide another list, and this time it's going to be, well, anything I want it to be really, but let's just say I use these values. And then I'll do the exact same thing with the printing so you can see the difference here. So I'll just do the exact same code, but print S2 instead of S1. And then I'll run this. And now you can see we still have the 1, 1, 2, 3, 5, 8. Those are the values. The first list to the series constructor, that is going to be the data. The second one is going to be the indices to use. As you can see here, it's 1, 1, 1, 4, 5, 6. Now, if this was a traditional dictionary or another structure which uses key value pairs, it would have only ever allowed a single 1 for one of the keys or one of the indexes. So in this case, it's allowing me to go beyond that and allow me to have multiple things associated with the same key or the same index. And likewise, notice I asked for the 4. It's not the fourth element necessarily. It's 0, 1, 2, 3. It is the fourth element, but if we were just counting like before, that would have been index 3. But now we said index 4, and it gave us back a 3. If I were to change that to like a 2, we don't have a 2 anymore. And it lets me know. It can't find it. Okay, key error 2. But what happens if I asked for the 1? What do you think we'll get? Yep, we get another series with the values in it. So if it only returns a single value, you'd get the single value. If you actually return a subset of the series, it returns another series. And that also brings up another point about what we're seeing at the bottom of the printout here where it says dtype int64. Now, int64 is a data type that is used more in other languages like C, where it specifies it's an integer style number and it's 64 bits wide, which if it was 32 bits wide, it would handle something like 4 billion possible values, but a 64-bit value, it's something I think to 18 zeros. It's a very large number. Okay, but as you know in Python, we're not supposed to have a limit to the size of our numbers. And so as soon as I exceed the ability to hold it in a regular numeric value, the data type went from int64 to object. Okay, so it tries to keep the values in the series as unified. In other words, it tries to find out what the most common attribute of these values are. But if I threw it like a string in here, then it has no choice but to convert the entire series into an object series, because you can't represent an A and a 2, which is a number, as the same data type. They are two different data types. There's this thing called object, which is basically any object can be stored in here, or any data type. And as I just demonstrated in one of these series, you can actually have whatever values you wish. There's nothing to restrict you from putting in strings. There's nothing that says you can't put in dates, whatever. It's the data you want. Now, this is going to be important because we are going to start using this later on in something called a data frame, and a series will typically represent a column of data. And that's why it tries to keep the values unified as the same data type, because if you think of a database, typically all the values in a given column, they should be the same data type. Now I'm going to create another series, but this time instead of numeric values, it's going to be date values. And the reason this is important is because a lot of businesses, schools, pretty much the whole world runs on the calendar. We have quarters, months, yearly things. We can look at your bi-weekly paycheck. All of these things we need to be able to model in any good data analysis program. And so we have a special date handling function called date range, which allows us to have a start date, a number of periods, and then a frequency that we wish for, basically the gap between each value that we're creating. So if we're starting on January 1st, 2019, I can provide a code here for the frequency of MS, which is monthly starting. Figure it's the first. Okay, if I left off the S, it would start with January 31st actually. And then I'll print dates 1. You can see it's going monthly. Now, I, by no stretch of the imagination, have all of these codes memorized. So I know about M. So if I run that, you'll see it's the 31st, and it's the end of every month. Let's put a Q in here. So end of the first quarter, end of the second quarter, end of the third quarter. And so there's actually quite a few codes that are available. And it's at this website, which you'll be able to locate in the documentation in class. But you can see here, if I wanted to do the start of the quarter, it'd be QS, just like month. To start the month is MS, or just the end of the month would be M. We can do weekly, we can do day frequency, etc. But let's say I wanted to skip every other month. I want to start in January 1st and then get to March. Well, I can provide M for the month, or actually SM, or MS, for the monthly start frequency. But I can also provide a multiplier. So I'll change this Q back to an MS, and I'll throw a 2 in front of it. Now when I run this, you'll see it starts on the 1st of January again, and then it skips every other month. So we have January, March, May, July, etc., all the way through November. And that was just by changing the frequency. So this would allow us, when we're analyzing our data, to start grouping data into whatever time spans we wish. And when we start looking at data frames and then of course graphing, this will come in very handy because it allows us then to specify discrete points on the calendar for our data values. So we can create another series. I'll call this one S3, and I'll set it equal to a new series, and this time we'll go back to using the series initializer again. But instead of providing a numeric list for both the values and the indices, I'm going to use another helper function. This one's coming from NumPy, and it is the random class random function that will generate a list of random numbers for me. And in this case, it's just going to be some value, I believe, between 0 and 1, 6 of them. And then I'm going to provide our calendar or our date series as the index. And I'm going to put it back to just MS to see that it's monthly. So let me rerun that one. And then I can print S3, and you'll see now the index values are calendar dates, whereas the values are just random numbers. So that's a really useful function. If you just want a random array of values, I can just do that. So I can say print, let's just call it R, and I'll set it equal to np.rand, random.rand. Let's say I want 10. And then I'll print R. You can see now I get a list of 10 values that are random. And there are multiple random functions in NumPy. There are some which will give you random values but along a distribution. So you are familiar with the bell curve used when describing things like standard deviation. Well, it can provide random values from that distribution. So if your peak of your distribution is around the value 0.5, then you'll get more values in your randomizer around 0.5 than you will around 0.1, okay, or 0.9 for that matter. Right now, I just use the standard random function, which should give us an even distribution between 0 and 1. So if you're interested in NumPy and getting more details about it, you would go to the scipy.org website, and I jumped all the way into the NumPy random rand reference to look at that random function. And as you can see here, the parameter I gave it, I just gave it a single value, which told it how many values to return. But I could provide several values, and that is just going to be the size of the dimensions of what I want the returns to be. So if I wanted a two-dimensional array where I had 2 values and 3 rows of them, I could specify 3 rows of 2 values. And now you can see it's row 1, row 2, row 3, and each of the values. And with rand, it is a uniform distribution between 0 and 1. So if you kept asking for numbers, eventually, you'll get an even number of 0.1s as you would 0.9s or 0.2s, etc., over a long enough span of tests. But there's also rand n, which is a similar random generator, except this one is going to use more of a bell curve to decide what values to return. And I'm not going to get into statistics in this particular course, but if you're interested in statistics, there are several different random sampling functions you can use. And then it also tells you, you can actually use this formula here where it says how many values you want. You have sigma and mu on either side. You multiply by sigma, and then you add mu. And this right here is basically going to be the center point where 50% of the values should be to the right of that and 50 should be to the left. And the sigma is going to help you define how wide that bell curve should be. So when you start going beyond 1 sigma, 2 sigmas, 3 sigmas, typically everything should fall, like 99.9% of the values should fall within 3 sigmas of mu here. So that's what these are for. Again, not a statistics course, but if you want something where you have weighted random values being generated, then this is probably the distribution you want. And you might be asking what I would ever use something like this for. Well, if you ever wanted to simulate the roll of dice, you could, and you have 2 of them. As you know, there are more ways to create the combination for the number 7 than any other number. So it goes anywhere between 2 and 12, but 7 is the most common number. So if you were to plot all the various combinations you can get between 2 and 12, it would look like a bell curve, where the center of the curve would indicate how many ways to make 7, and then the lowest part of the curves would be the 1 and the 12, because there's only one way to make each, either 2 1s or 2 6s. Okay. Now, if you didn't want to roll 2 individual die, in other words, use 2 random numbers to do this, you could use more of like this random standard normal distribution and just provide the range that you wish to get values for, and then it would actually end up giving you numbers that are closer to 7 most of the time, and then some stragglers out at 1 and 12. Again, I wasn't really going to get into the statistics in this, but I figured I'm here at least tell you some of it. Let's go back to the demo. Okay, so I generated just a random list of numbers. As I said, I could get like 3 rows of 10 if I wanted, or that's too many. Let's just say 3 rows of 5. You can see there's row 1, row 2, row 3, and this is a 3 by 5 array, so you end up with 15 values. Okay, so we're going to be using NumPy for many of our data analysis demos, just because some of the functions are extremely handy, especially for simulation. Okay, so we also know when we create a series that the series is some sort of data type. If you needed to know what the data types are, you could ask by saying like s3.dtypes. And that will tell you that they're float 64s, okay, the floating point numbers. Now, I know you're used to when you use type, it gives you back something like float or int or string. It doesn't actually give you this 64. So that's something you're going to have to get used to, is that these are typed values. They're strongly typed based on the C language. So it's a 64-bit float, which yields so many digits of precision. I think it's something like between 12 and 17. Somewhere in there is the resolution of a 64-bit float. It could be a little higher, but essentially it is good enough for most programs. Then I'm going to show you another series which does not have a consistent data type. So it might have an integer in there, might have a letter or a character, might have a float. I'm going to throw something in here called NP, not a number. So like infinity, it's not a real number. And then I'll ask what the data type of this is. Now, because of what we did earlier, you probably know the answer already. It's going to be object, because these are all different data types. They don't have anything in common, so it's going to force everything into this object data type where anything could be essentially anything. Okay? Then we also have the ability to name a series. I'm just going to call it stuff because it's just a random mishmash of things. It doesn't actually have any rhyme or reason. But now you can see when I print out the series, before when I printed out a series it just said the data type. Now I provided a name for the data type. So you can see the name is stuff, data type is object. So this allows me to store this kind of metadata with this series, and later, if I decide to use it as a column in a data frame, then I'll be able to utilize this name property to set the column caption and/or name itself. Now let's start working with the series, like putting values in, taking values out. Well, series are not really meant to be changed. And here's what I mean by that. If I were to say S5, and then we know we have an index of 1, and let me set that equal to 12. And then we'll print S5. Okay, it does actually work, but most of the time when you're dealing with a series or any of the stuff in Pandas, you don't want to change things in place. You really want to do functions that leave the original series or data frame alone and create a new one. And then you can chain these things together. Like I could assign a value here but use one of the function calls and then pass that to yet another function call, then another function call, so I can chain things together. This can't be chained together because this is a single statement. I can't say dot at the end of here and do something else. Okay, so method chaining is one of the reasons why a lot of these objects inside of Pandas will not allow you to change things in place. Memory management also has something to deal with it, or something to do with it. And the reason is when you create an array in C, the values are very evenly distributed in the memory. So if you create an array of 64-bit ints, every cell in the array is going to take up exactly 64 bits or 8 bytes. And therefore, it's easy to index into there because we know the fourth element is basically going to be at the index of 4 times 8 bytes away. Actually, it's probably going to be 4 minus 1 times 8 bytes away because it's zero-based. But it's very quick to get to the exact memory location of every value in there. But now if I start putting weird things in here, and these are objects, then it can't store everything in line in memory that way because it can't guarantee what the size of any of these values will ever be. Like 1 used to be a string with A in it, and now it's a 12. So strings and numeric values are very different in memory, and therefore it can't make an even distribution of the cells in memory. It just can't say automatically, if I have 6 values in there, I know exactly how much memory. If it was the N64s, which are 8 bytes each, and we had 6 elements in there, I knew then it was going to take up exactly 48 bytes. But now, because I have floats in there, I had strings in there, there's no way to know for sure how big it is. So it has to use some tricks behind the scenes where we still have a uniform size of the array, but the values now don't store right in the array. It's pointers to the values somewhere else in memory. Let's say I wanted to get a specific value out of the series. We already know we can access it by index, especially if it's zero-based like this. Even if it was a date such as this, if I asked for like the third element, the number 3, it would give me back this element right here, 0, 1, 2, 3. Okay, because it's not going to confuse the number I give it with the date. It's not going to have any issues. But let's say I had this series again. So I'm going to bring series 2 back down here, rerun it, reinitialize it, and then I want to get the element at index 1. What happens with that again? Print S2 1. Well, it gave me 3 values because 3 values had the index of 1. But no, what I really meant was I wanted to get this one here. This is element 0, element 1, element 2, element 3, 4, and 5. I wanted this one right here. Well, there is a method that you can call, which is I@, or the index at. I can provide S2 dot I@, and then give it the 1. And now when I run it, it gave me just the 1 that was stored at index 1. The slicers that we used with strings also work with series. So if I had my S5 series here, and I wanted to get a portion of that. Let's say I want to get the first 3 values out of there. Well, then I could say S5, and then the method I'm going to call is iloc, which is like index location, and I'm going to say everything up until the index 3, which should be 0, 1, and 2. I run that, and it does give me 0, 1, and 2, all the way to 3, 5, 2. And likewise, you can do it from the other direction. Instead of :3, I could say 3 colon. And now when I run this, you can see it gets me the rest. It starts at index 3 and returns everything after. Or you can use a very specific range. Okay, I could say 3 and 4. Then it's giving me starting at index 3 up to but not including in index 4. So all the standard slicer stuff works with these series if you use the iloc function. There are other useful functions such as, and rather than typing it out, I'll speed up the video a little bit here. You don't have to watch. We have this has nans. What that means is, does our series have a not a number value in it? If I hit run on this cell, you'll see it does. But if I did it on S2, if you recall, S2 is just all numeric values, and I run this again, now it's going to say false because there are no nans in that series. If I want, I can also do this right here. There's an index function, and the index function is going to basically give me information about how the indexes are stored. So you can see here it starts at 0, stops at 6, it steps by 1. That's for S5. Now, what if I did it for the one with the dates? That was S3. So let's do S3.index. So where the dates are the index. Now you can see that it's a date time index. It gives us all that information. What happens if I used S2, where we had multiple indices with the same value? Okay, now it can't break it down into like, well, it's a monotonically increasing list. It's skipping by 1. Now it's just, well, here's your index, because it's basically a random pattern as far as it's concerned. If you need to get the size of the series or the count of not a number values, we have those as well. So there's the size method and then the count. Now you can see here the size is 6 for S5, but the count is 5. So that means it had 6 values. If I look at S5 again, there are 6 values in there, but one of them is not a number. So if I just wanted the total number of elements regardless, then I'm going to use size. But if I want, I can use count, and that will tell me all the elements that have legitimate data in them. We can also determine how many values are unique. There's this nUnique function, which will say how many unique values are in there. In the case of S2, I would imagine there's only going to be 4 of them. So let's actually do S2 first. That's 5, actually. Let's see here. Did I fix this? S2 is this series. Oh, actually, I was looking at the indices, not the values. In fact, there are 5 that are unique. We have duplicates on the 1s. Okay, so that is correct. But let's change it with list of S5, and you'll see the difference in the way I'm calling nUnique. Once I call it with no parameter, and the next time I say drop NA as false. So that means it will count the NAs as actual values. So if I just say unique without saying drop NA as false, it'll come back with 5 values. The 1, the 12, 3.52, the 5, and the 8. However, when I say drop NA as false, then not a number is also a legitimate value. And that drop NA parameter is typically true by default, and it's available in most of these functions. You would actually have to look up the help to see which ones they are available in. But now I'm going to show you one final set of statistical functions so you can see some of the things built into the series, like what's the minimum value, what's the maximum value, what's the sum of all the values, what's the mean, what's the median, what's the mode. So all of these are functions you can call on a series. I created another one called S6. As a matter of fact, let's just put this in another cell. This is getting a little crowded in here. Okay, and I'll run that, and you can see in this list the first 8 Fibonacci numbers. The minimum value is 1, the maximum is 21. That looks good. The sum is 54. I'll take its word for it. The mean, or should I say the average, is 6.75. The median, or the centermost value, is a 4. And notice there is no 4 in here, but it's an even numbered list, so it takes the first and the second halves of this and looks what's the value directly in between the last number of the first half and the first number of the last half. Well, and guess what? That's a 4. So that's why it returns a 4. And then mode. And mode is the one that indicates which values show up the most number of times. Okay? And you can see here 1 is the number that shows up the most number of times. Now there are mathematical functions we can run on series as well. I'm going to create another series called S7, and I'll set it to equal to S6 add 2. Now what's going to happen here is it's going to take the S6 series, and then for every value in there, the 1, the 1, the 2, etc., it's going to add 2 to each of them and generate a new series. Let me run that. And you can see instead of 1, 1, 2, 3, 5, it's now 3, 3, 4, 5, 7. And so everything was added by 2. And likewise, I can also make this an S8. And instead of add, I'll do mul. And now it multiplied everything by 2. But you can also do it with another series or even a list. So let me take this mul, and this time I'm going to make another one, but instead of, I won't store it in another series, but instead of just passing a single value, I'll pass another list with the same number of values that are in S6, and when I run this, you'll see it multiplies the first one by 1, the second one by 2, the third one by 3, all the way to the last one where we multiplied the value by 8. So very useful if you have to basically meld multiple series together. But we can also create a function. I'll say def square, and this function is going to return x squared. I don't need a colon there. And then if I want to do a similar thing where I have the original list, let's start with S6 again, and then I'll say S9 is equal to S6 dot apply, and then I'm telling it apply this function to every value in the list or the series, and I run it. So now it took every value and multiplied it by itself. So 1 squared is 1, 2 squared is 4, etc., all the way up to this value 441, which if you look at S6 was 21 squared. So it's 21 times 21 is 441. You can also do it in line with the lambda. So I can just copy this, but instead of calling square, I could say lambda x such that x squared, and then print S9, and then you'll see we get the same results. So you can use a regular function in there, or you can use a lambda. Now, this is a long video already, and I've really only scratched the surface of series. As I mentioned, it's even more important you understand something called data frames, which is where you're going to handle basically series of data. Or think about it like a mini database.